Welcome to BioIT World's Trends from the Trenches podcast, your insider's look at the science, technology, and executive trends driving the life sciences. I'm Allison Proffitt, editor of BioIT World. This episode is hosted by Stan Gloss, founder of BioTeam, a life sciences IT consulting company at the intersection of science, data, and technology. Today, Stan talks with James Cuff, who recently came out of retirement to serve as Chief of Scientific Computing and Partnerships at GIGALO. They cover the industry, discussing cloud computing, on-prem data centers, networking, edge computing, AI, staffing, and more. Let's listen in.
Good morning, James. It's so nice to talk to you.
Hi, morning, Stan. Good to talk to you too.
Yeah, it's been a while, so we have a lot to talk about today. But, maybe we can start by having you tell us a little bit about your background for those of you, for the few people in this world who don't know who you are.
Bless you. So it's about a 25-year span of career. I worked at the Wellcome Trust Sanger Institute, the Broad Institute of MIT and Harvard. I did a stint as the center director at Harvard University, where we built a pretty much world-class HPC facility from scratch. And then recently attempted to do an early retirement, but given that I'm on this podcast with you, we know how all that went. So,
and we will definitely address that issue towards the end. But maybe we can start off just by, you just explained a long career background over the years. Maybe you can kind of walk us through the evolution of how things have changed technologically from where you started to where we are.
Yeah, that's a great question, and time to reminisce a little bit. So I think if I was to actually start where my career really did computing at scale was for the human genome at the Wellcome Trust Sanger Institute and the European Bioinformatics Institute. We had to stand up inordinate amounts of compute in a very significant hurry to be able to inform and annotate the human genome very, very rapidly. And at that time, there were very few options available. And so it was then where I really learned the spirit of the Beowulf computing concept by taking commodity off-the-shelf computing resources, networking them together. This was before the days of software orchestration, so there was some very exotic little shell scripts to be able to build these machines and get them up so that we could run our genome annotation pipeline. And it's kind of interesting as the career evolved, a lot of things stay the same, and some of the things change and update. But we're still in a world where the coupling together of disparate computing resources is still a priority and is still a challenge for us as a species to be able to get our most difficult and complex pieces of science to execute. And I think if I look back and think of how computing has evolved, we absolutely have more of it than we ever have. We are fortunate that computing now threads its way through all of our life on a daily basis. And yet we are still in a situation where we are still bounded by computational complexity, be it either access to storage, is it access to more sophisticated computing resources. And so if I was to sort of summarize the career arc, computing hasn't actually gotten easier, albeit portions of it are a little more straightforward than they used to be. Well, for example, we don't use janky Perl scripts to orchestrate our compute anymore.
So that's interesting. I think we always seem to be working towards the next bottleneck in our designs, and that's always on a moving target, trying to hit one bottleneck. If you have too much data generation, then you don't have enough compute. If you have too much compute. And so what's your notion on managing to the bottlenecks that we're facing today?
Yeah, I mean, it's a sort of the scientific principle, really. If you can't measure it, you can't fix it. And I think a lot of the challenges that pop up in very complex computing environments, certainly where you've got a lot of heterogeneity in the environment, you have to effectively put the measuring stick in your compute by taking your actual running workloads. And workloads evolve. I mean, my experience of running shared computing resources for tens of thousands of disparate users, each workload was sufficiently different from the next workload that it's very hard to tune systems to be perfect. And so one learns the art of compromise very, very early on in your career to be able to make sure that the systems are good enough, fit for purpose. Perfection is the enemy of the good, right? I mean, and at a certain point, finding an IO bottleneck in a workload is often quite a cathartic experience. You feel good as a provider of services to be able to locate and isolate those IO challenges. And sometimes it's not just a case of throwing dollars at the problem. You actually have to think through how your workload is being partitioned, the job granularity, how the data are being ingested and analyzed, and it's quite a serious job to be able to make sure that the machines are operating at capacity, because it costs money to power and energize and cool these devices, and you have to spend a lot of time trying to make sure that you're getting the best return of investment on your significant either capital or operating budget, and whether those resources are local to you or if they're in a hyperscaler data center, the same game applies, whether you're paying by the hour or whether you're signing large capital checks to be able to get lorry loads of equipment into a data center. And so I think that as we look and look at the world writ large in terms of energy and sustainability, there's a direct impact on the unit of science as to the true cost of what that unit of science costs. And these are not invisible costs. They're absolutely real. It costs energy to generate energy, and those computing devices, as we keep seeing, are becoming more and more energy intensive. And as a provider of compute, you have to be very aware of how your algorithms are actually working and working optimally. And I think that's also important when people are acquiring compute, either, as I say, by the hour or making capital purchases, that the benchmarks and the initial qualification of those computers are done carefully.
That's terrific, James. You've had a unique perspective now because you've been in semi-retirement. We can all just sit back and kind of pay attention to the market because we have our jobs to do. But you've had some time to really kind of take a look at the marketplace from an independent point of view. I'd love to pick your brain on what are some of the hottest trends or the trends that you're seeing in infrastructure, like specifically on infrastructure. So, maybe you could give us some insights on HPC and storage, and then we'll talk a little bit more about some of the other areas.
Yeah, thanks, Stan. I mean, it was nice to be able to sit and reflect and ruminate in an independent way. I've had to subsequently tone down my Twitter to make sure that I'm no longer independent. But yes, it's fascinating to me. I mean, and I think once a technologist, always a technologist. And I've had this sort of passion for understanding how computing can help society, right, at a high level. And what does that mean at an infrastructure point of view? We used to stand up fiber channel storage arrays. We had, proliferation of NFS and early object store systems that were, let's call them fragile, to be kind. And at scale, storage is one of those very gnarly, difficult concepts to as a person delivering a storage as a service. And I think, what has changed and what really gives me great promise is at the hyperscalers, they've managed to build very sophisticated object stores and very intricate networks to be effectively eliminate the headache of storage, right? And so in comparison to that, what's happening in the industry is the file systems are finally getting to a point where you can effectively purchase a subscription for your storage, and you will know that it will work. It will just work. I was talking to an academic colleague the other day who picked a particular type of storage, and he just said, I just don't worry about it anymore. And I find that really, really heartening, that these long-formed headaches are slowly going away, allowing the researcher to focus more on, their actual scientific output, and not having to worry about availability or scalability of their storage. Sure, there will always be workloads that, let's say, challenge the storage environment or challenge the network, and that's all part of LifeSwitch tapestry, and will continue to happen. But I'm seeing that the evolution of the core processing elements, the fact that the processes that are within network filers, be they distributed storage or be they more traditional enterprise scale storage providers, they're just so much better, which is good, because sometimes we feel that computing evolves and we sort of feel like we're sitting in the same place. But I've seen things come on leaps and bounds, and there are a lot of good industry leaders who aren't selling the old storage story, which is heartening to me, and it's coupled around advances in the software that enables you to consume these storage elements.
That's fantastic. So what about networking? Paying attention to that?
Yeah, absolutely. I mean, we were standing up science demilitarized zones to be able to remove friction for the researchers to be able to collaborate. And so, we were seeing Internet 2 standing up 100 gigabit networks. The challenge there is often in the data transfer nodes and being able to ingest at such high speed. It's quite remarkable. A few years ago, when we first stood up our first networks, I was finding difficulty finding enough friends on the academic network to talk to. But with the investments, these nodes are now omnipresent, and so that's at the edge of the network. Within the data center, we've seen low latency, high bandwidth networks really come on leaps and bounds, and so we've seen this evolution from DDR InfiniBand speeds all the way up now, where you're getting 200 and 400 gigabit per second networks that are able to not only shift data at high speed, but also do it with very low latency, such that your round trips in and out of storage or for your message passing algorithms will be more highly performant. And this is where we were talking earlier of the bottleneck. As we're generating much more high-powered silicon, and we're able to write very small feature sets down to the sort of nanometer scale. We can pack billions of transistors on a processor. But the old adage is you've got to feed it, and being able to make sure that the balance between your latest and greatest highly performant multi petaflop computing device, has to get data in and out of it. And what I'm starting to see in the industry is folks are starting to do more joined up infrastructure and selling solutions, and the types of providers that are in the market that are able to package solutions is of great importance, and certainly the hyperscalers have dramatically bent the curve in terms of what you can get access to. Elastic fabric adapters, InfiniBand adapters now available to rent by the minute, are really changing the types of compute that folks are able to do. Certainly either grand challenge problems or be able to very quickly. I spent a while as the CTO at Cycle Computing, right? And we were at that time using spot instances to be able to generate huge molecular dynamics runs, for sort of pennies on the dollar, right? Because you could get in, compute, and kind of get back out again. And that's a specific class of problem. In the large academic high-performance computing centers, you're seeing how their service delivery is changing too. And so how they connect themselves to the internet backbone, is very important. And people are thinking more about computing being far away, right? Whether it's a national center, even as a center director up in the northeast here at Harvard, we built a data center that was in Western Massachusetts next to hydroelectric. We had sustainable power, low cost energy. But it's a 200-mile round trip,
Right.
And so you have to start thinking about compute and data locality differently, and then couple that with highly performant parallel file systems. Your architecture and your design principles for compute are evolving, right? I mean, and I think locality is no longer, the data closet, down the corridor. You're thinking much more in terms of global computing resources, and so the network's even more important now. It's certainly in terms of. But when you get into security aspects, right, you have to have DPUs, you have to have hardware cryptography on your network to make sure it's safe and secure, and all of those kind of things, which are new headaches for everyone to wrestle with.
Right. So it's interesting when you mentioned the concept of computing being global. During the pandemic, we had all kinds of supply chain problems, and a lot of. Thank God we had the backup of being able to go to the cloud. So many of our clients that we talk to are moving to the cloud. Have you been watching any of that activity?
Yeah, no, absolutely. I mean, I think there's a push me, pull me in the world, and we're seeing both vast adoption of cloud computing, but also on the other side, to be completely agnostic, we're seeing data repatriation and certain data sovereignty challenges that will always pop up. And I think I always think of cloud as a business model, not necessarily a technology. And I know that's kind of slightly controversial, and in the sense that it comes down to a business decision. At a certain point, there are very good and rich application programming interfaces to be able to interface to cloud services and be able to move data in and out. But we're also seeing a rise within the research computing community to be able to provide cloud-like services by exploiting the economies of scale. There's a different cost model when you have an on-premise storage and computing infrastructure. And again, academics, your FTE costs are sometimes marginal for those great salaries that they pay in academia, right?
Right.
And so there's this sort of push me, pull me, and I see both sides of this argument, but I keep coming back to the same thing. Benchmark your application, do the sums. I think I was fortunate. I argued to make sure that the energy budget was actually part of my CapEx and OpEx spend at the university. And so I was incentivized to make sure that the compute that I was running was as low cost as practically possible. And it was also folded in. So effectively, I was running an entire, sort of cloud business with our team, right? And so my economies of scale were always different. And it comes down to the use case. And I've sold on-prem, I've sold cloud, and a whole thing that is consistent standards. Whichever one I was selling, folks wanted the other one.
Isn't that always true?
I try and keep religion and politics out of it and business proposals out of it. Benchmark your application, look at your science, make your choices. The same ways we always have done, be it either an on-prem or off-premise solution. Bench your code, work out who the vendor of choice is, and make your selection, and stick with it. I'm not a hybrid multi-cloud conceptual kind of guy. I go where the science takes me.
Right. There's a term that is floating around called edge computing. Do you run into any of that kind of approach?
Yeah, certainly. Yeah, certainly in the new day job for sure. But we're seeing compute start to move into locations where you wouldn't necessarily expect to see it. Think of telecommunications as a classic use case. Our cell phone providers now are no longer just selling us voice messaging services, right? So there are a whole series of layered products that go out to the cell phone towers and have to be managed and delivered. And so we're seeing a lot of complexity there in terms of how the telco providers are providing their quotes edge service, but also in the scientific community. I did some work on the scientific advisory board for the Earlham Institute, and it's Earlham is in Norwich. It's a prestigious genome sequencing and annotation center. They put together the wheat genome, which, and it turns out wheat was an awful lot more complicated than we thought, and you needed quite a lot of resources. But what I saw in the scientific program there was the researchers are starting to effectively instrument the farmer's field. And you're starting to see this instrumentation of devices that end up it's amazing how much data can come out of a field. Right. So, you're starting to have to think about, locality of compute in all sorts of weird and interesting ways. And so, to me, the edge is more of an ability to try and massage your data, before it comes flooding back to the data center. I mean, an autonomous vehicle is a classic, edge use case, right? You can't afford to have enough bandwidth to be able to do that. The type of life safety compute that needs to happen, in your vehicle. And so, and it's also interesting. We've been working with folks that do their networking inside of motor vehicles, and it's quite interesting. You get in a car and you turn it on, it boots immediately, right? There's none of this, waiting for the BIOS or right. loading from disk. That would be a pretty miserable experience in terms of the type of compute that would happen at that edge. Yeah, nobody's going to sit around waiting for their car to boot.
That's right. So it's really interesting, all this technology that you've talked about and how things have evolved. What about let's talk a little bit about the people, because the skills that you required 20 years ago aren't the skills you need today, and probably are not going to be the skills you need tomorrow. So how do we manage the skill set of the equation?
Yeah, it's a great question, Stan. We made some good strides whilst I was at Harvard. We got money from the National Science Foundation to look at what we were calling advanced research computing cyber infrastructure facilitators. Never let academics come up with acronyms. It always ends up quite a mouthful. But what's actually happened over the last 5 to 10 years is this evolution of the research software engineer. And the research software engineer is quite possibly the most compelling construct we have in modern scientific computing. These are superhuman individuals that sit between, the infrastructure and the compute and the research scientists. And they're able to really help wring out both performance and scalability out of traditional high-performance computing centers and working in close collaboration with the research scientist. And that role was never really professionalized. There was always a local IT nerd, that may be found in the basement. I remember at Manchester University, the crystallography department, had someone who knew how the VAX worked, and they were this sort of almighty bearded creature. It was sometimes not always the most pleasant of environments, because these individuals were often underpaid and overworked and trying to effectively spin 1,000 plates on the end of sticks every day. And I think the thing that gives me great hope is seeing the professionalization of the research computing scientist as a fully fledged first-class citizen of the scientific process. We're not 100% there yet, but there are some great programs, nationally and internationally, that are really championing this new type of scientist that's part of the research computing ecosystem. And it's no longer just about building bigger hyperscaler environments or larger computing centers, and we're seeing the science and research foundations starting to invest in that. And of course, you talk to any scientist, more needs to be done, of course. Yep. But I do see that, and I think it's even more important as our software complexity continues to rise and continues to scale. Having folks that are fluent, in the language of computing, but also more importantly about the service delivery aspects of computing. And traditionally, service delivery humans have not necessarily been treated the best way that they could be. Right. And I, for one, welcome the investments and the support of those people. They're vital to our success.
Well, with those skill sets, I would love to pivot over to the one topic that we haven't touched, but maybe we can briefly touch on the rise of AI and ML, and I'm sure you've been tracking that as well.
Yeah, I mean, it's here. It's a thing. I mean, my PhD was in neural networks for protein structure prediction, and I look at the types of neural networks I stood up versus what is available today, and it's almost as if it's a different language altogether. We use the same words, but the complexity of the deep neural network is staggering, and the types of digital twins that are being demonstrated, and the types of work that folks like Jensen Huang at NVIDIA is pushing on the world are truly remarkable. You're looking at whole Earth simulation, right, being done on these massive computers. One has to take, as all things, there's a level of skepticism. Just because one has a hammer, not everything is a nail, and it will evolve. But I'm seeing some, interesting use cases where folks are starting to think about replacing some complex multiphysics codes. It's going to be interesting, and I think Fernando Forte said it the best. Just be aware of what folks are really selling you, right? I mean, and be a healthy skeptic, but there's, you look at the AlphaFold code. It works, right? I mean, I'm just mad I'm not in that field anymore, because I think it's quite exciting. And to be able to draw a line and say protein structure prediction is solved in my lifetime, I remember the last line of my PhD. It was like, I don't think we're going to do any better than this. I was wrong.
Right. So James, I'd like to end up with one, like the $64,000 question that I and a lot of people would love to ask you, which is, you joined an organization called GIGALO and came out of retirement to do that. Could you tell us a little bit about the company and why you came out of retirement to go to GIGALO? I'd really like to know.
Thanks, Stan. Yeah, no, it was quite remarkable. I mean, I'd spent, as I say, 5 or so years still connected to the industry, did some consulting gigs and so forth. And thank you for asking all those earlier questions. I was watching what was happening. And I started to get this bug around composability and disaggregated compute, because every system I've ever built or borrowed or rented has always been inherently the wrong shape. And I've always struggled trying to make sure that the right computing is available for the right researcher at the right time to solve the right problem. And so, to give a 10,000-foot view of what GIGALO does, is that they are able to effectively virtualize hardware resources. You can put any accelerator with any chunk of memory and any chunk of storage under any type of compute. The way they do that is that they strip away the complexity of host adapters and speak the true native language of the computer, which is PCI. And so we are able to connect computers both at very high bandwidth and exploit the by16 Gen 4 networking capability of PCI, but we can also do it with low latency. And not only can we juggle those resources around to build what we funnily call impossible servers, we're able to actually pass messages between these devices so that you can, at a higher level, start to do MPI, you can share storage, you can start to share memory. We're part of the CXL consortium, and we're watching how the Express Link is evolving. And we have product today that can solve people's problems. The product of tomorrow is really why I joined the company. And my job title is as Chief of Scientific Computing and Partnerships. And that part of the partnership is a very important part of my day job, is being able to advocate and evangelize why people should care about both composable computing and thinking about computer architectures in a different way. So yeah, I'm psyched. It's been a wild month ride. I've met some really stunning hardware engineers who work with us. Great software team too, because you can't do hardware without software.
Right.
And I'm excited for the next chapter, and it also scratches all of my itches because it's everything about the computing career that I've had kind of wrapped up with a little bow on it, and it's exciting. So yeah, thanks for asking the question, Stan. Appreciate it.
Yeah, it sounds like we're going to have to come back to you in a little while and see what you've learned and see what you've done. But anyway, James, thank you so much for joining me today and sharing your experiences with our audience. And hope we can do it again sometime soon.
Thanks for having me, Stan. It's always a pleasure. Good to talk to you.
Cheers.
All right, cheerio.
This episode was produced by Pete Glowacki and myself, Allison Profit, with the BioIT World media team from www.bioitworld.com. It was hosted by Stan Gloss, founder of BioTeam, a life science IT consulting firm at the intersection of science, data, and technology. BioTeam builds innovative scientific data ecosystems that close the gap between what scientists want to do with their data and what they can do. Learn more at www.bioteam.net.